Every year, billions of people around the world touch chromium on faucets, cars, appliances, and almost no one realizes that behind this cold shine lies one of the most dangerous chemicals in modern industry. How can a metal that makes steel stainless and withstands jet engine temperatures simultaneously poison water, air, and the workers who handle it? In this video, we'll step behind the doors of mines, furnaces, and electroplating tanks. Witness how gleaming surfaces are born from toxic dust and molten metal, and by the end, reveal a property of chromium that even many engineers don't suspect. Watch through to the finale, and you'll never look at an ordinary chrome-plated faucet in your own bathroom the same way again. Chromium is a metal that simultaneously attracts with its shine and intimidates with its dangers. In pure form, it displays a cool silvery blue color, exceptional hardness, and polishes beautifully to an almost mirror-like surface. It's precisely this thin layer of metallic chromium on parts that gives us the familiar chrome look, from pickup truck bumpers to bathroom faucets. A coating just a few thousandths of an inch thick can transform ordinary steel into a brilliant, visually premium material that also resists corrosion better. But beneath this gloss hides a complex technological chain and toxic chemistry, especially during the mining and ore processing stages. The primary source of chromium is the mineral chromite. It's extracted in quarries and mines, where the rock is drilled, blasted, crushed, and sorted. Dust from the ore contains chromium compounds in various oxidation states, and some of them are toxic to the lungs and skin. So mines and processing plants require serious dust and gas cleaning systems, along with personal protective equipment. After crushing, chromite undergoes enrichment, flotation and gravity separation, to separate the valuable mineral from waste rock. Concentrate with chromium content above 45% is sent to blast furnaces or electric furnaces, where at temperatures exceeding 3,600 degrees Fahrenheit, it's reduced with carbon to produce ferrochrome, an alloy of iron and chromium. It's ferrochrome, not pure chromium, that serves as the main workhorse for metallurgy. The majority of all extracted chromium goes into producing stainless steels. If you add 10 to 26% by mass of chromium to molten carbon steel, an extremely thin but highly resistant oxide film forms on the surface. It self-heals when damaged and protects metal from rust even in humid or aggressive environments. That's how we get kitchen sinks, railings, medical instruments, and chemical reactor tanks that maintain their appearance for years. Imagine a chemical storage tank holding several thousand gallons. Adding chromium to the steel allows it to withstand contact with solutions that would have corroded ordinary structural steel long ago. Another crucial area is heat-resistant alloys. Chromium increases heat resistance and wear resistance, which is why it's incorporated into steels for turbine components, nozzles, and internal combustion engine valves operating at temperatures exceeding 1500 degrees. Combined with nickel and cobalt, these form so-called superalloys used in jet engines and power plants. Where steel must withstand both high temperatures and powerful mechanical loads, chromium is nearly indispensable. Even ball bearings in high-speed machine tools contain chromium steel, so the raceways don't break down from impact and friction. Chromite is also used without converting it to metal. It's made into refractory materials for furnace linings, where temperatures reach 3,000 degrees. A mix of chromite and magnesite aggregates withstands sudden temperature changes and contact with slag without breaking down. These linings cover the walls of cement rotary kilns, converters, and smelting units in ferrous and non-ferrous metallurgy. Chromite sands are used as molding mixtures in foundry work. They don't react with molten steel, have minimal thermal expansion, and allow casting of complex parts with high precision. One of chromium's most recognizable facets is the shine of electroplated coatings. The chromium plating process is electrolysis, where a part made of steel or another metal is immersed in a chromium salt solution and current is passed through the bath. A thin layer of metallic chromium settles on the surface, ranging from a few micro-inches in decorative coatings to several thousandths of an inch in industrial chrome plating. The thin layer provides aesthetic shine and basic corrosion protection. For example, on automotive trim, tool handles, and plumbing fixtures. Thicker layers are used to enhance wear resistance. Hydraulic cylinder surfaces, piston rods, press molds, and printing press rollers. These components work in contact with abrasive materials and fluids under high pressure, but thanks to the hard chromium layer, they maintain their dimensions and geometry much longer. However, it's precisely during the chrome plating stage and the production of chromium salts that the element's toxicity becomes most acute. Hexavalent chromium, present in certain electrolytes and reagents, is a carcinogen and can cause damage to the skin, mucous membranes, and respiratory tract. That's why modern facilities are implementing closed-loop purification systems, automated plating baths, and localized ventilation, while some industries are gradually switching to trivalent chromium or completely different types of coatings. Many countries enforce strict limits on chromium compound concentrations in workplace air and wastewater, and sludge containers are stored in specialized landfills to prevent toxic ions from leaching into groundwater. Equally fascinating is chromium's role in the colors surrounding us. This element's compounds produce vibrant greens, yellows, reds, and oranges. Chromium oxide serves as one of the most stable green pigments for ceramics, road markings, and paints that must withstand sunlight and weathering. Chromates and dichromates once provided brilliant yellow and orange pigments widely used in artist paints and printing, but due to hexavalent chromium's toxicity, their use is now strictly regulated or replaced with safer alternatives. Nevertheless, in some highly specialized materials, such as ceramic pigments for tile, chromium compounds are still used to achieve the desired shade and color stability during firing. The chemical industry relies on chromium, both as a catalyst and as an active reagent. From sodium dichromate and other salts, a wide spectrum of chromium compounds is produced, which are applied in the manufacturing of textile dyes, mordants for fixing dyes onto fibers, and agents for leather tanning. Traditional chromium tanning makes leather resistant to water, rot, and abrasion, but carries the risk of forming toxic chromium species, so modern manufacturers are transitioning to controlled processes with minimal emissions or alternative systems. Chromates were once included in anti-corrosion primers for aluminum aircraft and ship parts. They suppress the development of corrosion sites, but due to their toxicity, they too are gradually being replaced by less hazardous technologies. Interestingly, in microdoses, trivalent chromium is considered a trace element that may participate in regulating carbohydrate metabolism in the human body. But even here, the working concentration is measured in micrograms per day, and exceeding permissible levels, especially when in contact with compounds, takes on a toxicological rather than biological character. That's why chromium is one of those elements where the fine line between benefit and harm literally runs through an order of magnitude in concentration. If you look at the industrial map of the world, chromite mining centers are located in South Africa, Kazakhstan, Turkey, India, and several other countries. Ore from there travels to metallurgical plants, chemical factories, and electroplating shops, being transformed into stainless steel, heat-resistant alloys, refractories, pigments, and coatings. Products fly across the globe, from kitchens in American suburbs to oil rigs in the Gulf of Mexico, and jet airliners crossing continents at 30,000 feet. The gleam of chrome surfaces in your bathroom, or on a car hood, represents just the visible tip of the iceberg, beneath which lie mines, furnaces, electrolysis baths, and strict environmental regulations. Every year, over 50,000 tons of uranium are mined worldwide. But to get just a few grams of energy from it, you have to move mountains. It all starts in the desert, where the temperature reaches 100 degrees and ends in a reactor that powers New York. Here, centrifuges that spin faster than an airplane turbine, and substances that corrode metal in seconds. But the most interesting part is what even safety instructions don't talk about. Watch until the end, and you'll discover a secret that will change your perception of nuclear energy. It all begins in the dust. And that's not figuratively speaking. Uranium ore is mined in hot regions: Arizona, Wyoming, Texas, New Mexico, sort of like cowboy landscapes, only instead of lassos, there are drilling rigs, and instead of a sheriff, engineers in anti-radiation suits. The sun here is scorching, up to 100 degrees Fahrenheit in the shade, if you can find any. There are two ways of mining. Open pit, where the top layer of soil is removed and the ore is pulled out by excavators, and underground mining, with explosives, lifts, and ventilation that howls like an old tractor. And there's also the in situ leaching method. Pipes are driven into the ground, and special solutions are pumped in to wash out the uranium directly from the rock, and then it's pumped back out. All this ore, a grayish-brown rock, looks no different from ordinary stones. But in it, uranium-235 is only 0.7%. The rest is almost useless mass that doesn't work in a reactor. And to squeeze the needed drop of energy from it, you have to process hundreds of tons. That's why they say nuclear energy is quite a marathon. After mining, the ore is crushed, ground, and thrown into a chemical bath. Acid or alkaline solutions are added to extract the uranium, like coffee from a filter. Then, filtration, precipitation, drying at 500 degrees Fahrenheit. And at the output, yellowcake, a yellow powdery concentrate. The official name is natural uranium concentrate, but everyone at the plants just calls it yellowcake. It looks beautiful, mustard-colored, fluffy, like a spicy powder for barbecue. But God forbid you inhale or touch it. Alpha radiation, a long half-life, dangerous dust that penetrates the lungs and settles there forever. People work with it only in respirators, suits, behind 3 layers of glass protection. Yellowcake is packed into double-walled barrels, loaded onto trailers with an escort, and wrapped with radiation signs. And off it goes to the enrichment plant. It's from this poisonous dust that the journey begins, leading to the white light of a lamp over a kitchen table, or the electricity in the subway rushing under New York. Well then, yellowcake is here, in barrels, radioactive and dry as a desert wind. The next step, turning it into a gas. And not just any lavender-scented gas, but uranium hexafluoride, the very same from which the required isotope for reactors and more is later separated. Let's cook, baby! The uranium concentrate is first dissolved in acid, purified, filtered from impurities, and converted into uranium dioxide. And here the magic begins. Uranium dioxide is treated with fluorine in special reactors at a temperature of 1000 degrees Fahrenheit. And as a result of the reaction, a volatile, transparent gas is formed, which boils at 133 degrees Fahrenheit. That is, you just need to heat it a little, and it turns from crystals into vapor. But it's not that simple. It is extremely toxic. It corrodes metals, destroys skin, and in humid air, it immediately turns into hydrogen fluoride and uranic acid. That is, a deadly cocktail. That's why all this is done in sealed, automated reactors that look more like devices from a villain's laboratory. Temperature, pressure, ventilation, everything is under control. Workers sit behind thick windows, monitoring the sensors. Any mistake, boom, or hiss, and you're already in a hazmat suit, scratching your heels on the way to the shower. This substance forms as solid whitish crystals when cooled to room temperature. These crystals are stored in steel containers, barrels with engravings, a batch number, and a radioactive sign. Each one weighs under 14 tons. And so, mission accomplished. The dust is turned into gas, ready for the most interesting part, isotope enrichment. But don't rush to celebrate. This gas is like a wild cobra. Beautiful, shiny, but if it bites, no one can save you. You think spinning a washing machine is fast? You haven't seen nuclear centrifuges that do 70,000 revolutions per minute. That's 10 times faster than an airplane turbine. And all for one thing, to separate uranium isotopes. The fluorine-enriched uranium dioxide, that same poisonous gas we just made, is pumped into a tall, narrow cylindrical chamber, which is spun up to an insane speed. Centrifugal force does its thing. The heavier U-238 atoms fly to the edge, while the lighter U-235 atoms stay closer to the center. A tiny, microscopic difference, 1% in mass, and all this explosive technology spins just for it. But one centrifuge is not enough, so they are connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas, then passes it to the next, and so cycle after cycle, until the U-235 content becomes at least 3 or 5%. This is the reactor standard. For weapons, of course, completely different routes are taken. They are classified and under strict international control. Okay, the gas is enriched, but in its gaseous state, it won't feed a reactor. So now it's converted again, this time into a solid ceramic form. After a series of chemical reactions with hydrogen, oxygen, and ammonia, the gas becomes uranium dioxide, a solid substance with a dark gray color. This powder is pressed under a pressure of 20 tons into small cylindrical pellets with a diameter of 3/10 of an inch. They look almost cute. But each such pill is like a charge of energy equivalent to 17,000 cubic feet of natural gas. Next, the pellets are sintered in furnaces at almost 3,000 degrees Fahrenheit to make them strong, like porcelain. Then they are polished, ground. Perfect dimensions are important for a tight fit in the cladding. The pellets are placed in long metal tubes, fuel rods, usually made of a zirconium alloy, because it doesn't rust, doesn't react with water, and withstands insane radiation. Over 300 pellets are placed in each rod. The rods are hermetically welded and combined into modules, fuel assemblies. They look like a frame of several dozen tubes, assembled in a square. One such assembly can weigh over 1,500 pounds and works for up to 6 years in a reactor. After assembly, testing for leaks, uniformity of filling, weld integrity, behavior under temperature. There are no trifles, because each of them can cost not just money, but lives. The finished fuel is packed in armored containers that can withstand impacts, fire, and falls from a height. Transportation is under guard on a special route with an escort, GPS, and mandatory. 2 seals, 3 codes, and a dosimeter on each side. Because even in its peaceful form, this is a dangerous thing that commands respect. After all this, what remains is depleted uranium hexafluoride. They call it tails. It's a mixture of isotopes where there's still a bit of uranium-235, but not much. These tails are stored in steel drums on special sites under supervision. But in the future, they can be reprocessed in new generation reactors, where everything will be squeezed out to the last drop. When a fuel assembly has served its 4 or 6 years in the heart of a reactor, it's no longer the shiny star it was at launch. It is removed, carefully, with a robotic system, and moved to pools of water. The depth is over 20 feet. The water cools and shields the radiation because the fuel is still hot, physically and radioactively. There it rests for several years. Then, 2 paths, either long-term dry storage in concrete containers with double walls, or reprocessing. In other countries, because the US mostly stores rather than reprocesses. In dry storage, the cassettes stand for decades, cooled by natural ventilation, as if in a nuclear monastery. This is not the end, but a new stage of life. Slow, controlled, but deeply connected to the future of energy. Because even after the reactor, this fuel remains a source of heat, a lesson, and a reason for respect. Every hour worldwide, there are dozens of nuclear reactions, but only a few know that at the heart of every atomic bomb is a material capable of destroying a city in seconds. This isn't just a weapon, it's a miniature star, created by human hands. You will learn how ordinary uranium gives birth to an explosion with the force of thousands of suns, why the sand in New Mexico turned to glass, and what happened to an island that no longer exists. And most importantly, what secret is hidden inside a nuclear warhead? Watch until the end, because the finale will change your perception of the modern world. In ancient times, when the world was just learning to hear the voice of the atom, a few curious minds peered into the invisible, into the heart of matter. Those were the years when science was fumbling in the dark, but with great aspiration. German chemist Otto Hahn, along with Fritz Strassmann, like alchemists of a new world, discovered uranium can be split. It was like ice cracking on a river, under which a giant was sleeping. While Europe was preparing for war, a group of people, later to be called the Lords of the Atomic Flame, secretly gathered across the ocean. The Manhattan Project began in the New Mexico desert. Ordinary physicists, Oppenheimer, Fermi, Teller, became the creators of the greatest force humanity had ever seen. In the summer of 1945, under the dawn clouds, the first nuclear bomb exploded. The sand turned to glass, the sky to fire. And amidst the complete silence, one scientist whispered, "Now I am become death, the destroyer of worlds." But the story didn't end there. A few days later, Hiroshima and Nagasaki became pages of sorrow. And when the world thought it had seen everything, the USSR responded. Under the leadership of Igor Kurchatov, the first Soviet atomic bomb exploded in 1949, and a decade later, the Tsar Bomba. Its power could destroy a city the size of Paris. The irony of history is that nuclear weapons became not a sword, but a shield. Their existence forced enemies to talk. The ideas of security, control, and diplomacy became more important than combat. For the first time, humanity posed global questions. Can we agree to survive together? Thus, the doctrine of deterrence emerged. Do not attack, because you know that an attack will turn into a catastrophe. And although this balance can hardly be called ideal, it provided decades without a global war between superpowers. An entire era, cold, anxious, but without massive fronts. Nuclear research gave birth to new fields: nuclear energy, reactors on submarines, medical diagnostics. Even space projects received a boost thanks to the understanding of the atom. To create the most terrible, we learned to comprehend the most complex. Yes, nuclear weapons are a danger, but they are also a mirror of human wisdom. We created something super powerful and did not use it on a massive scale. This is a story about a force that we decided to restrain. About a science that taught us not to dominate, but to coexist. In the depths of laboratories, where the light of lamps dimly illuminates blueprints, the journey to creating a nuclear bomb begins. This is not just an assembly of metal. It is the alchemy of modernity, where every gram of substance has the power of 1,000 suns. It all starts with uranium or plutonium, isotopes capable of sustaining a chain reaction. But uranium in nature is mostly uranium-238, which is not suitable, so it is enriched. The 235 isotope is separated using centrifuges, where gaseous uranium spins at insane speeds. Plutonium is artificial. It is obtained in nuclear reactors, where uranium absorbs neutrons and turns into the plutonium needed for a nuclear bomb. The external appearance of a nuclear bomb often resembles a classic aerial bomb, a streamlined metal body designed for stable descent from a great height. In a huge hangar, where the walls ring with the echo of metal, the air smells of hot steel and lubricant. Here begins the birth of the shell that must contain the heart of the atomic explosion. From the red-hot maw of an industrial furnace comes a stream of metal, a special steel, reinforced with nickel, chromium, and manganese. Its temperature is over 1,000 degrees Fahrenheit. The summer sun pales in comparison to this fire. Masters, in protective suits with transparent shields, watch the forming. On presses with a force of hundreds of tons, a steel sheet is bent into a streamlined shape. Before their eyes, an elongated body is born, resembling a drop of water, frozen under the pressure of the heavens. Next, mechanical arms mill internal partitions. Cut holes for tail stabilizers and locks. Every millimeter is the result of careful calculation, because the balance during the fall depends on it. After this, the body undergoes a strengthening ritual: immersion in an anti-corrosion bath, treatment with a polymer coating, and a matte paint finish. The color is dark green, similar to a military shadow on a slope of pines. And finally, testing. It is dropped from a height, struck with hammers, rotated in a wind tunnel. A quiet laboratory, semi-darkness, a light smell of ozone. Something heavy hangs in the air. Before you lies an open nuclear bomb, its metal walls removed, and its insides, like an organism, lie exposed. There is nothing superfluous here. No shine, no decorations. Only function, only explosion. At the center, a smooth, perfect sphere. It looks like a dull meteorite. This is the nuclear charge. Plutonium-239, cold and deadly, or uranium-235, heavy as a planet in the palm of your hand. Its shape is mathematical perfection, polished to the micron. Around this sphere is a whole symphony of pressure. Composite explosives, layer by layer, resemble a flower, folded inside out. Their task is not just to explode, but to make the explosion happen inside. Like palms squeezing to the limit, these explosive lenses must create an implosion, a uniform, ruthless compression that will make the substance supercritical. If even 1 second is delayed, the entire structure will become a meaningless pile of metal. And in the very heart of this implosion orchestra, the initiator, a small device waiting for the moment to release the first neutrons. Polonium and beryllium interact, creating a tiny storm capable of starting the irreversible. It is from this that the chain reaction will begin. A match to an atomic forest. Then, a layer of tamper. Heavy as a shadow, it envelops the heart of the bomb, not to protect, but to contain. Uranium-238 or tungsten are not active, but extremely important. Their task is to delay the neutrons, to make them return, like an echo in a cave. The duration of the explosion, its power, its apex, all depend on this. In the tail of the body, the brain. Automation, electronics, wires and sensors. Barometers await altitude, radars watch the ground, batteries slumber, ready to awaken. Here it is decided when everything must happen. Over a city, in the air, after the fall. Without this nervous system, the explosion would be an accident. But here it is, a calculation. If you look at the entire structure in cross-section, it resembles the layers of a planet, the sections of an encyclopedia of power. The outer casing, smooth and cold, the layer of explosives, mathematically arranged, the tamper, an invisible guardian, the core, like the seed of the future, and in the very center, a spark that sleeps until it is awakened. In 62 years, 2,065 nuclear explosions have occurred in the world. 5,224 is not the number of nuclear explosions, but an approximate estimate of the total US arsenal, including active, reserve, and dismantled warheads. But the number of nuclear tests that the US conducted from 1945 to 1992 is 1,154 explosions, and each of them is a separate page in the history of power, fear, and science. The first explosion, Trinity, on July 16, 1945, in the New Mexico desert. This was the beginning of an era when the energy of the atom became a weapon. It was followed by Hiroshima and Nagasaki, the only instances of the combat use of nuclear weapons. In the following decades, the US tested bombs on the atolls of Eniwetok and Bikini, in Nevada, underground, in the atmosphere, and over water. The explosions had different purposes. Testing new designs, demonstrating power, studying the effects on technology and living organisms. The power varied, from a few kilotons to 15 megatons, as in the Castle Bravo test of 1954. In 1952, the US conducted the first thermonuclear test, Ivy Mike. This was no longer just a bomb, but a miniature star created by man. The explosion destroyed an entire island. In the 1960s, testing became regular. The US tested warheads for missiles, aerial bombs, and even neutron charges, which had a minimal blast wave but maximum radiation. The last official explosion took place on September 23, 1992, after which the US declared a moratorium. But the arsenal remained. It is being modernized, adapted, and maintained. Some warheads are on submarines, some on strategic bombers, and some in NATO storage facilities. These explosions are not just technical events. They are a story of how humanity learned to control the energy of the stars and put it at the service of fear. Imagine this. Every year, the world produces over 100,000 tons of titanium, a metal that has become a true symbol of innovation and strength in aviation, space, and energy. It's from this metal that the story of creating ultralight and super strong alloys begins, used for manufacturing the most critical parts of airplanes, rockets, and even geothermal equipment. In America, where titanium production technologies have reached the highest level, this metal has become indispensable in creating the future, combining lightness with extraordinary strength. Next, I'll tell you how titanium is born, from raw material to a high-tech material that is changing the world. The history of titanium production begins at the end of the 18th century, when in 1791, a British clergyman and amateur mineralogist, William Gregor, discovered a new metal in the mineral ilmenite, which is now the main source of titanium. Initially, this metal was called menaconite, but later, in 1795, the German chemist Martin Klaproth rediscovered the element in the mineral rutile and named it titanium, in honor of the mythical Titans, giants of ancient Greek mythology. However, pure metal was first successfully obtained only in 1825 by the Swedish chemist Berzelius, although at that time it was contaminated with impurities and practically unsuitable for industrial use. The first attempts at industrial production of titanium began only in the 20th century. In 1910, the American chemist Matthew Hunter obtained a small amount of pure titanium, and a real breakthrough occurred in 1925 when Dutch scientists Van Arkel and de Boer developed a method for obtaining high-purity titanium, which opened the way for its widespread application. From the mid-20th century, titanium production developed intensively, especially in the United States, where the metal became indispensable in aviation, the space industry, and the military industry. The production of titanium begins with the extraction of titanium-bearing raw materials, mainly the minerals ilmenite and rutile, which contain titanium oxides. These ores are found in the form of placer or primary deposits and are widely distributed throughout the world, particularly in Australia, Canada, China, Norway, and South Africa. After extraction, the ore undergoes complex multi-stage processing. First, it is enriched, separating the titanium minerals from the gangue, obtaining ilmenite or rutile concentrates. Then, the concentrates are subjected to chlorination, which results in the formation of titanium tetrachloride, a volatile substance that is purified by distillation. This process allows for the removal of impurities and the production of a high-purity intermediate product. Next, titanium tetrachloride is reduced with magnesium or sodium in special reactors at a high temperature in an inert atmosphere, producing spongy titanium, a porous metal powder. This spongy titanium is then subjected to pressing, melting, and casting to obtain ingots or blanks for further processing. The production of titanium is energy-intensive and expensive due to the complexity of technological processes and the need to work in high-purity conditions. The main industrial method for obtaining titanium is the Kroll process, which remains the standard in the world. It includes chlorination of titanium ore, purification of titanium tetrachloride, and its reduction with a metal, which makes it possible to obtain high-quality metal for aviation, space technology, medicine, and other industries. Thus, the production of titanium begins with the extraction of ilmenite and rutile, goes through complex chemical reactions and physical processing to transform natural minerals into a high-tech metal that combines lightness, strength, and corrosion resistance. The initial stages of titanium production are based on a complex multi-stage technological process that begins with the extraction and preparation of titanium-bearing raw materials, primarily ilmenite and rutile. These minerals contain titanium oxides, which must be converted into chemically pure titanium tetrachloride. For this, concentrates of titanium ores are subjected to chlorination in fluidized bed reactors at a temperature of 1,800 degrees Fahrenheit, where carbon and gaseous chlorine react with the raw material, forming titanium and carbon monoxide. This tetrachloride contains impurities of other metals, which are removed by distillation, obtaining high-purity technical titanium. The next key stage is the reduction of titanium tetrachloride to metallic titanium. The most common industrial method is the Kroll process, in which titanium tetrachloride reacts with magnesium in a vacuum chamber at a high temperature. As a result, spongy titanium is formed, a porous metal powder that contains impurities of magnesium and magnesium chlorides. This reaction mass is subjected to vacuum distillation to remove impurities, after which the spongy titanium is pressed and remelted into solid ingots or slabs. The resulting titanium ingots are then used for the production of alloys, rolled products, sheets, and complex parts. The entire process requires strict control of purity, temperature regimes, and safety, as titanium actively reacts with oxygen and nitrogen when heated. Just look at how incredible it is. A porous, light, and seemingly fluffy mass of metal. This is spongy titanium. It looks nothing like a regular metal bar, but rather like a piece of metal sponge or foam, only made of titanium. But this fluffy material is the first step towards creating strong and reliable titanium ingots, which are then used in aviation, medicine, and other high-tech industries. First of all, titanium ingots can be used to create titanium alloys, mixtures of titanium with other metals that improve its properties. To obtain an alloy, alloying elements are added to molten titanium, most often aluminum, vanadium, molybdenum, iron, or niobium. These impurities change the metal's structure, increase its strength, heat resistance, corrosion resistance, and improve its processability. The production of alloys usually takes place in vacuum arc furnaces, where the metal is melted at high temperatures in a protective atmosphere to avoid oxidation. To achieve a homogeneous composition, the alloy is remelted several times, and after that, it is cooled and prepared for further processing. The next stage is rolling. Ingots or slabs of titanium and titanium alloys are heated to a certain temperature to make the metal more plastic, and passed through special rolls. Rolling allows for reducing the thickness of the metal, giving it the required shape and size, as well as improving its structure and mechanical properties. As a result, various types of rolled products are obtained: strips, ribbons, wire, and bars. Rolling can be hot or cold, depending on the requirements for the final product. Sheet metal is made from rolled products, thin, flat blanks that are widely used in construction, aviation, medicine, and other industries. Titanium sheets are characterized by high strength and corrosion resistance, and are also easily subjected to further processing, cutting, bending, and stamping. The production of sheets requires precise control of thickness and surface quality, so after rolling, they are often subjected to additional processing, such as polishing or anodizing. To create complex parts, various methods of processing titanium and titanium alloys are used. These can be mechanical milling, turning, grinding, as well as modern technologies such as additive manufacturing using laser powder bed fusion. Additive technologies allow for the creation of parts with complex geometry that are impossible to produce using traditional methods. This is especially important for the aviation and medical industries, where lightweight, strong, and precise components are needed. In addition, to improve the performance characteristics, titanium products can be subjected to heat treatment, annealing, quenching, or aging. These processes change the internal structure of the metal, improving its strength, hardness, and fatigue resistance. In aviation, titanium is used to make up 15% of the weight of a modern passenger aircraft, which significantly reduces its overall weight and increases fuel efficiency. In the medical field, about 70% of implants, such as artificial joints and dental prostheses, are made from titanium or its alloys due to their biocompatibility and durability. Every year, over 2 billion tons of asphalt are produced worldwide. But there's a place where even road pavement is an engineering art. Imagine, in the middle of a desert, under a 120-degree sun, asphalt is born that doesn't melt, doesn't crack, and even reflects light. How do oil residues from a tanker turn into a super-modified mixture that withstands sandstorms? And what do the RTA laboratories in Dubai hide? If you watch until the end, you'll find out what they never tell you in promotional brochures. It all begins on the waves of the Persian Gulf, where giant tankers slowly cut through the water's surface, carrying millions of barrels of black gold, crude oil. It travels from Iraq, Saudi Arabia, Kuwait, countries where sand and fire have intertwined in an eternal dance of energy. When a tanker slowly docks at one of the UAE ports, for example, at Jebel Ali, one of the largest man-made ports in the world, an act begins where technology and people work as a single organism. Oil, having just completed a transcontinental journey, is pumped into huge tanks, like into concrete hearts. These tanks, hidden in the industrial landscape, are the beginning of the transformation, where raw material becomes the essence of civilization. Next, it travels underground, in pipelines, like arteries leading to oil refineries. In Jebel Ali or Abu Dhabi, it is met by reactors, distillers, chrome columns, and heating furnaces. There, it is heated to a temperature of over 660 degrees Fahrenheit to separate it into fractions. Light components, gasoline, diesel, kerosene, evaporate first. The heaviest residues, which do not evaporate even at high temperatures, are exactly what will become the basis for asphalt. This residue is called heavy fuel oil or vacuum residue. It is fed into a vacuum column, where the pressure is reduced to a minimum, allowing for the separation of even more light fractions without thermal destruction of the heavy molecules. What remains after vacuum distillation is bitumen, a black, viscous substance that is the basis for asphalt. Bitumen itself is too thick and rigid for use in road construction, especially in desert conditions where temperatures can reach 120 degrees. Therefore, it is modified. In special reactors, it is mixed with polymer additives, plasticizers, stabilizers, and sometimes even rubber crumb. This process is called bitumen modification. The result is a material that has high elasticity, resistance to ultraviolet light, does not soften in the sun, and does not crack at night when the temperature drops sharply. In Dubai, polymer-modified bitumen is mainly used, which meets the standards of the RTA, the Emirates Road Agency. When bitumen completes its transformation in specialized reactors, acquiring elasticity, heat resistance, and the ability to withstand the infernal desert sun, a new stage of its journey begins: delivery to asphalt mixing plants. The modified bitumen from the reactor enters heat-insulated tanks that maintain its temperature at approximately 350 degrees Fahrenheit. In a liquid state, it maintains its homogeneity and readiness for mixing with mineral components. Then, it is pumped by high-pressure pumps into sealed pipelines leading to the plant. Or, if the plant is located at a distance, it is poured into tank trucks with special thermal containers. Such tankers are built with a double steel body, with an insulating layer that prevents the bitumen from cooling during transport. The road to the plant is like the roots of a city's circulatory system, where every drop matters. The drivers of such bitumen trucks undergo special training. They must maintain a stable speed, avoid sharp braking, and monitor temperature sensors in real time. If the temperature starts to drop, heating is activated so that the mixture does not lose its properties. At the plant, for example at DXB Asphalt Factory in Dubai Industrial City, the tank truck enters a receiving complex where it is connected to the unloading system via reinforced thermal hoses. At this moment, the bitumen is hot, thick, with a characteristic smell reminiscent of a mixture of rubber and metal. It is pumped into intermediate mixing tanks, where it waits for dosing. From this moment, it becomes part of the recipe, in a formula where the weight, viscosity, and temperature of each component determine the durability of the future road surface. One of the largest is the DXB asphalt factory in Dubai Industrial City. There, bitumen is heated to 320 degrees Fahrenheit and mixed with mineral aggregates: gabbro, basalt, quartz, sand. Gabbro is a dark volcanic rock mined in the mountains of Fujairah. It has high density and strength, which makes it an ideal aggregate for road pavement. The stone is crushed into fractions smaller than an inch, sifted through vibrating screens, dried in drum dryers, and fed into a mixer. In the mixer, bitumen and aggregates are combined into a hot mass called hot mix asphalt. The temperature of the mixture is 320 degrees Fahrenheit. It must be homogeneous, without lumps, with a precise ratio of components. For this, automated dosing systems are used, which control the weight of each ingredient. After mixing, the asphalt is fed into silos, where it is stored for no more than 6 hours so as not to lose its properties. From there, it is loaded into dump trucks with thermal insulation, which deliver the material to construction sites. On site, the asphalt is distributed over the surface using asphalt pavers, machines that evenly spread the mixture on the roadbed. Then it is compacted with rollers, first vibrating, then static. In the desert, it is important to achieve maximum density to prevent the penetration of sand and water. Therefore, compaction is carried out in several passes, and the asphalt temperature during paving must be at least 250 degrees Fahrenheit. If it drops, the mixture loses its plasticity, and the road will quickly deteriorate. A feature of Dubai's highways is that they have a multi-layer structure. The lower layer is coarse-grained asphalt, which provides load-bearing capacity. The middle layer is made of modified bitumen, which acts as a shock absorber. The top layer is a thin layer with a polymer coating, which provides grip with the wheels and resistance to abrasion. In some cases, light-reflecting minerals are added to reduce surface heating. In the desert, it is important to consider not only temperature, but also dust, wind, and humidity fluctuations. Therefore, asphalt plants in Dubai are equipped with air filtration systems, and the mixtures themselves are tested for resistance to abrasive wear, thermal expansion, and even sandstorms. In the RTA laboratories, each batch of asphalt is checked for viscosity, density, water absorption, and thermal stability. If the indicators do not meet the standards, the material is returned for reprocessing. This process, from a tanker of oil to a finished road, takes several days but requires dozens of control stages. And it is thanks to this that Dubai's highways withstand the load of thousands of cars every day, do not melt under the sun, and do not crack at night. Asphalt here is not just a black mass, but an engineering system that combines oil, stone, polymers, and desert endurance. Over 1 million tons of asphalt are produced annually in Dubai, and this figure is growing along with the expansion of infrastructure. The DXB asphalt factory alone has a capacity of 240 tons per hour, which allows for supplying large projects without interruptions. For comparison, an average plant in Europe produces about 150 tons per hour. Interestingly, asphalt is the most recycled material in the US, and over 99% of old pavement is returned to production. In Dubai, recycling is also being actively implemented, especially during the reconstruction of old roads in industrial areas. And from which country are you watching us? Every year, thousands of miles of new railway tracks get laid down all over the world. But the Japanese, they've turned it into a true art form. Here, rails the length of a football field are born from the molten lava of steel, reaching over 2,700 degrees Fahrenheit. They're joined together to seem absolutely endless, and the concrete track slabs, as thick as 2 footballs, hide the secrets of eternity and speed. So how did the Shinkansen engineers manage to achieve that almost perfect, smooth ride? An average delay of just 36 seconds and speeds of up to 200 miles per hour? Watch till the end, and you'll find out something you'd never have guessed. We're stepping into a massive Japanese steel mill. The atmosphere is thick with heavy air, a mixture of heat, steel, and the deep hum of powerful machinery. In front of us is the main star of the show, a steel-making furnace the size of a 5-story building. It looks like the tongue of a volcano, glowing a dazzling white hot. Inside is a boiling mixture of iron and carbon. Its temperature is over 2,700 degrees Fahrenheit. The molten metal pours out with a roar into special molds, like a bright orange river of lava flowing down a mountain. The workers look absolutely tiny against the backdrop of the huge machines. After the steel is melted in that huge furnace, it gradually starts to cool, turning from a liquid into a solid but still very hot piece of metal. This piece, think of it as a thick, hot bar several feet long, is then fed into a rolling mill. A rolling mill is a gigantic machine, kind of like a huge meat grinder, only instead of a blade, it has heavy steel rollers that press and stretch the metal. The dull roar gets even louder as the machine grabs the red-hot blank. With a sound like a deep groan and the scrape of friction, the hot metal begins to stretch out, like dough for pasta, but not soft, dense and heavy. Gradually, this bar becomes longer, thinner, and more uniform, and eventually, it transforms into a long rail, 320 feet in length. That's like a football field and then some. The surface of a rail like this has to be perfectly smooth, without the slightest ripple. Because if it's even a little bit uneven, the high-speed Shinkansen train won't glide smoothly over it. It'll start hopping at the joints, like a little frog in a swamp. After rolling, the rail is still incredibly hot. Steam rises from it, and you can hear a crackling sound, like when water hits a hot stove. But this is almost its final form, long, heavy, smooth, ready for inspections, grinding, and its future, becoming part of the track for one of the fastest trains in the world. To reduce the number of joints, which are potential spots for wear and noise, Japan uses a method of continuous welded rail. That's when several rails are joined into one incredibly long strip, almost 5,000 feet long, making the rail seem endless. Welding rails for high-speed trains like the Shinkansen is a high-precision technological process. The goal is to turn individual rail sections into a single, seamless strip up to almost a mile long. It's this type of connection that lets them avoid the traditional clickety-clack sound when going over joints, reduces wear, and creates that smooth gliding effect. The welding process happens in several stages. Most often, they use thermite welding, a reliable and pretty spectacular technology. 2 rails are placed end to end, so a gap of a few millimeters is left between them. The surfaces of the future joint are thoroughly cleaned of rust, scale, dust, and any other contaminants. It is crucial that the edges of the rails are perfectly even, like knife blades before being joined. Next, a special mold made of a sand mixture or a heat-resistant material is mounted around the joint. It holds the molten metal during the reaction and gives it the required shape. A thermite mixture, a powdered mix of aluminum and iron oxide, is poured into a small container above the joint. When it's ignited, a reaction occurs, during which a temperature of over 4,500 degrees Fahrenheit is released. As a result, molten iron is produced, which flows down and fills the gap between the rails, joining them at a molecular level. The reaction takes several minutes. During this time, you can hear hissing and crackling, and a bright flame rises above the joint. It looks just like a miniature volcanic eruption. After the metal solidifies in 10 minutes, the mold is removed, and the excess metal is trimmed off. The joint is then ground to a perfectly smooth surface, so the train wheel doesn't feel the transition from one piece of rail to another. The finished joint is checked with laser measurements, as well as with ultrasonic sensors that look for any possible microcracks. A rail like this is installed as a single, solid block and has a minimal number of service points, which lowers repair costs and the risk of delays. In a world where every second is precious, Shinkansen engineers discovered the secret to eternity: slab track. Instead of traditional stone ballast that crumbles under the pressure of time, they created monolithic giants out of concrete. These titan-like slabs reach a thickness of 26 inches. That's the height of 2 footballs stacked on top of each other. The Japanese masters came up with a genius solution: encapsulation elements. Imagine a metal cradle that hugs the rail like a mother holding a child. These cradles not only hold the steel guides, but also isolate them from vibrations and electricity. It's like giving the rails superpowers, the stability of Superman and the flexibility of a dancer. The most genius part of the whole system is what you can't see. Between the concrete slabs and the foundation, the Japanese placed resilient layers that act like giant shock absorbers. In tunnels, slab track works true wonders of economy. A lower track height means a smaller tunnel cross-section, which reduces construction costs by a fantastic 30%. Transporting the sleepers to the installation site is done in several ways, depending on the distance and accessibility. Transporting sleepers by road requires special measures to prevent any movement during transit. Transporting sleepers by rail must be carried out according to a loading plan approved by the railway department. For short distances, special trucks with cranes are used. For long routes, railway flat cars are used. Safety during transport is critical. One concrete sleeper must be lifted by 4 workers, which highlights their significant weight, approximately 165 pounds per worker. For mechanized lifting, special grippers and cranes are used to avoid damage to both the sleepers and the workers. At the construction site, the installation process begins with preparing the foundation. For slab track, which is primarily used on the Shinkansen, the sleepers are installed on pre-prepared concrete slabs. Each sleeper is positioned with an accuracy of 1/4 of an inch, since even minimal deviations can cause problems at speeds of 200 miles per hour. The installation is carried out by specialized crews using precision equipment. First, support points are installed every 2 feet, the standard interval for high-speed lines. Each sleeper is attached to the base with special 1-inch diameter anchor bolts, which are driven 6 inches deep into the concrete slab. The process is complicated by the need to integrate with the power supply and signaling systems. The sleepers have special channels for laying cables, as well as insulators to prevent short circuits of the traction currents. Installers must consider the location of all engineering systems, including drainage channels and grounding. The final stage includes installing vibration isolation pads between the sleepers and the foundation. These rubber steel elements significantly reduce the transmission of vibrations from the trains to the surrounding structures. After the installation is complete, the entire section is tested by a special measuring train that moves at speed and records the slightest deviations in the track's geometry. Even with over 120,000 trains running on the line each year, the average delay is just 36 seconds. Over half a century, the speed has increased from 130 miles per hour to 200 miles per hour, and the passenger flow is now 1 million passengers a day. A new line is expected to be operational at a speed of 310 miles per hour, with an estimated travel time between Tokyo and Osaka of 67 minutes. Construction began in 2011, was initially planned to open in 2027, but is now postponed until at least 2034. Every year, over 130 million tons of glass are produced worldwide, a weight equivalent to 1.3 million Eiffel Towers. Imagine, mountains of broken glass, taller than skyscrapers, are transformed into crystal clarity thanks to fires of 3,000 degrees and laser snipers that knock out impurities at a rate of thousands of shots per minute. From ancient glassblowers who breathe life into red-hot bubbles, to futuristic tin baths where glass is born perfectly flat like a mirror. But behind this symphony of fire lies a secret. What if glass holds the secret to eternal reincarnation, which will allow us to turn the world upside down? Watch until the end, and you'll find out something you never imagined about this transparent, amazing material. Ready for the journey? Although the vast majority of architectural glass today is born from a perfectly flat, fiery river flowing over molten tin in the float process, the true soul of the material is revealed in methods that give it character and uniqueness. This path from a simple transparent sheet to a work of decorative art is a fascinating journey. To create glass with individuality that carries the imprint of a human touch, masters still turn to techniques that have existed for centuries. A glass blower dips his long, hollow pipe into a furnace where a mass of sand and other minerals boils at a temperature of 2,000 degrees Fahrenheit. He gathers a honey-like ball of molten glass on the end of the pipe and, skillfully rotating it, begins to blow air into it. The initial bubble, born from his breath, gradually transforms into an elongated, glowing hollow cylinder. Thanks to the force of gravity and skillful swinging, this cylinder can reach a length of several feet. After the ends of the cylinder are cut off, it is cut lengthwise and placed back in the furnace. There, under the influence of heat, it slowly unrolls, like a scroll, and the masters smooth it into a flat sheet. Glass born in this way is never perfectly flat. It lives its own life, retaining barely noticeable waves, tiny air bubbles, and thin lines that tell the story of its fiery birth. This glass has a watery, organic quality that cannot be replicated by a machine. But the creation of unique glass does not stop at forming the sheet itself. Other methods transform ordinary sheets into complex decorative elements. Fusing or sintering allows artists to literally paint with glass. Multicolored pieces of glass are laid out on a base sheet and sent to a furnace, where at a temperature of 1,500 degrees Fahrenheit, they merge into a single whole, creating bright, painting-like compositions. Closely related to this is the process of slumping or bending, where a flat sheet of glass is heated until it becomes soft and sags under its own weight, taking the shape of a ceramic or metal mold lying beneath it. This allows for the creation of curved panels and three-dimensional glass sculptures. Modern technologies add even more possibilities. Lamination allows for baking colored films, fabrics, or even thin sheets of metal between two sheets of glass, creating endless variations of color and texture. Sandblasting and chemical etching remove the top layer of glass, making it matte and creating complex patterns on its surface, from simple geometric shapes to photorealistic images. Thus, by combining ancient crafts with advanced technologies, modern production transforms simple glass into an expressive architectural material, capable of shaping light, color, and space. In the modern world, where tons of used glass containers are collected daily, the path from the trash can to a new bottle is not just remelting, but a high-tech odyssey, controlled by computers and light. Imagine a mountain of broken glass, reaching a height of tens of feet, where transparent, green, and brown fragments are mixed with labels, caps, and ceramic impurities. Turning this chaos into pure, raw material is a task for a whole complex of smart machines. It all starts with mechanical crushing, where steel hammers turn bottles and jars into fragments a few inches in size. This stream of glass, resembling a moving river, embarks on a journey through a labyrinth of sorting systems. First, powerful magnetic separators pull any steel impurities from the stream, and then eddy current systems literally shoot out aluminum caps and foil into separate containers. Powerful air currents blow away light paper labels and plastic remnants. But the most difficult task lies ahead: removing impurities that are almost indistinguishable from glass in weight and size, such as pieces of ceramics, stone, or porcelain. These enemies of glass do not melt at standard temperatures and turn into defects in new products, so their removal is critically important. This is where optical sorting comes into play. The glass fragments are accelerated on a conveyor belt to a high speed and fly through a scanning zone. For a fraction of a second, each fragment is illuminated by bright light, and high-speed cameras take hundreds of pictures. A computer system with lightning speed analyzes the images, identifying foreign bodies by their transparency, structure, and shape. As soon as the system spots an opaque piece of ceramic, it instantly calculates its trajectory and gives a command to a battery of air nozzles. A precise, sniper-like stream of compressed air knocks the unwanted element out of the general stream, sending it to waste. This process is repeated thousands of times per minute. In parallel, an equally important sorting by color takes place. The same optical systems analyze the spectrum of light passing through each fragment. The machine distinguishes between crystal clear, rich green, and deep brown glass. Depending on the set program, the system can, for example, select only transparent glass, knocking out all colored fragments with air jets, or separate the stream into 3 separate color fractions. As a result, at the output, a perfectly clean, color-sorted raw material is formed. Cull it, ready for a new life without loss of quality, which is the pinnacle of the modern circular economy. Then, flat glass can be made from this raw material. The birth of modern flat glass is a symphony of fire and precision, a spectacular process that transforms ordinary raw materials into perfectly transparent sheets. It all begins in a huge melting furnace, the fiery heart of the factory that operates continuously for years. Into this furnace, resembling a lake of molten fire, a carefully dosed mixture, or batch, is loaded, consisting of pure quartz sand, soda ash to lower the melting temperature, and limestone for stabilization. To this is added a significant amount of cullet, or crushed recycled glass, which helps to speed up the melting process. Inside the furnace, at infernal temperatures approaching 3,000 degrees Fahrenheit, these solid components slowly transform into a homogeneous, viscous liquid. The melting process is strictly controlled to ensure the complete dissolution of all particles and the removal of gas bubbles, creating a flawlessly clean melt. From the furnace, this stream of red-hot to bright orange-colored glass, resembling a river of lava, smoothly flows into a bath of molten tin. This is the culmination of the process, known as the float process. The tin bath, stretching for hundreds of feet in length, has a perfectly smooth, mirror-like surface. Since glass is lighter than tin and does not mix with it, it spreads over the surface, forming a perfectly flat ribbon of uniform thickness. Gravity levels it from below, and surface tension smooths it from above, creating impeccable optical quality. The speed at which this ribbon is pulled from the bath determines its final thickness with an accuracy of a fraction of an inch. After forming a perfectly flat surface, the glass ribbon, still very hot but already solid enough to hold its shape, enters the most tranquil but critically important stage: annealing. It enters a long tunnel known as an annealing layer. If the glass were cooled too quickly, its surface would contract faster than its interior, leading to the creation of huge internal stresses that would make it brittle and prone to cracking. In the layer, however, the temperature of the glass is slowly and controllably reduced over several hundred feet, from over 1,000 degrees Fahrenheit to room temperature. This process allows the entire sheet, both surface and core, to cool evenly, relieving all internal stresses. From the other end of the layer emerges a single, flawless, continuous ribbon of completely transparent, stress-free glass, ready for automatic cutting into huge sheets that will become the windows, facades, and doors of our world.